So Steve will discuss the application of OODA as a framework for securing OT systems. The OODA loop is the cycle of observe, orient, decide, and act, which I'm sure Steve will get into. But I remember that coming from the U.S. Air Force. So I'm excited to hear how that applies to operational technologies as well as industrial control systems and autonomous vehicles from the perspective of both the computer network defense and attack. So, Steve, thank you for joining us, and welcome to the GRIMMCon stage.
All right. Yeah, so I'm Steve Griffing, and we're going to look at what the heart and soul of OT systems are and how that, and do a little bit of history on conflict resolution. So first off, Steve Griffing, I'm from Booz Allen. A little bit of my history looks a whole lot like a whole bunch of Navy stuff, both active duty and reserve, and doing government contracting. All right. But when we think about it, what is the most vulnerable? We think about going for those crown jewels, the target, but sometimes that's not really the crown jewels aren't the decisive point. That's not what turns the battle. And so we need to focus on what the center of gravity, that thing that will actually turn the battle, and understand that cybersecurity is a conflict between two aggressive, antagonistic actors, your defense and your offense. We're not just one-sided. And a lot of people lose sight of that. But even though we do a lot of the red-blue teaming, some of the mindsets on how we build and design systems and think about them don't take into account that back and forth and that learning. So anyone who's done some theoretical level strategy might recognize this guy from the early 19th century. Clausewitz wrote the book On War, and one of the principal things that came out of that was the concept of a center of gravity, a single point from which all the conflict turns. And if you put pressure on that one point, you can turn a battle, you can turn even from a specific battle, even to a war. But for example, one of the things like from the Civil War, the Battle of Gettysburg, how it turned the entire war around and changed because it was a decisive victory for the federal troops and a decisive failure, a decisive loss for the rebellious states. And this comes back to the heart and soul of cyber physical systems, and all OT and ICS or autonomous vehicles, they all live and breathe this decision cycle, which as a controls engineer, this is our bread and butter. You have the controller, the automated system, whether it be a PLC or a embedded processor or what, makes some decisions and influences the final control elements, those wheels or actuators, motors, which then drives the process in a physical environment. And then the measuring happens with the sensors. And that loop goes around and around. And the heart and soul of it is making sure that that loop stays intact. So if you attack, you can attack any of those parts, but making an attack that actually corrupts that loop is much more significant than a momentary disruption of one of the elements, because it is a loop that self-corrects. It comes back to norm, and it's designed to. But it's also just like in interpersonal relationships, you always are wanting feedback from the one you're communicating with, to make sure that what you intended to say actually had the appropriate effect on your audience. And it's the same loop. Now, back in the 1980s and 90s, Colonel John Boyd developed his OODA or OODA loop that goes through observations, which are that sensor inputs, and making sure that you have good inputs. Then the orientation is all of that code that the control engineer builds his ladder logic or his Arduino sketch or other similar process to write and take all those observations from the sensor and match them up to the desired set points of the system. And then it goes through the decision. Okay, what options, what registers am I going to turn on? Which registers am I going to turn off? Which motors am I going to activate at which values? What speed? What direction? And then that action is the action of those final control elements and then whatever that action does, how it affects the system, understanding that environment will drive that loop to that observation again, where we have that closed loop, self-correcting design. But Boyd's thought process was not just on a control system, but on a conflict and the decision cycles, decision elements of those who make them, who make those choices and drive the conflict to a desired end state. But as you can see, it matches what we have, what I showed was the heart and soul of all operational technology systems. Now, let's go on to what has been modeled and theorized, how an attacker is going to attack an OT system. And we'll start off with SANS, pretty excellent cyber kill chain. And they show how a remote attacker goes through the steps to get in from the internet through a series of barriers to have a physical effect. The limitation of this is that it only shows one path to victory. Whereas if you're looking at the crown jewels as actually disrupting and denying that process from taking place, this does not show options like a partial bypassing it with coming in via a physical attack and then plugging in locally. This assumes that you come in the enterprise internet and or you have or your target is limited to just disrupting and taking over that process. Whereas if your target scope is wider, there are other ways, as we saw with the Colonial Pipeline, for instance, disrupt other portions of the business model, but still had the effect of shutting down the OT plant. And this does not, and more fundamentally, there's no feedback here. You always have to go from the planning all the way through stage 1 and then stage 2, and there's no way to bring your lessons learned or take in other people's advances to basically flank in. It's not accounted for. And that's a weakness of the cyber kill chain, but not just the cyber kill chain, but the linear causality attack models in general. And you can see the difference between this and something like the cyclical nature of the decision cycle in closed loop feedback or in Colonel Boyd's OODA loop. Okay, I'm going to quickly touch on the MITRE attack because it has been referenced as an alternative to the cyber kill chain to address some of those nonlinear challenges. And it does to some extent, but it is not fundamentally, and it was never made to be a flow, to describe the flow of an attack or the way that attacks perform. But it is a database of various options at various points along a roughly linear course. But it does take into account that there are other various options at each of those linear points. But it still doesn't address the constant learning and constant process improvement of a systems model of an attack or of the systems themselves, which are the target. Now, MIT did a much better job. An earlier speaker mentioned that there is a bit of crosstalk between the safety and hazard analysis community of interest and our security community of interest. And this comes from that safety area, but it also combines that with a solid understanding of system theory and the controller to process feedback loop that builds and closes in and makes and corrects itself to a desired state. And so building on this foundation, this brings us into that realm. But once again, this has its limits because it was designed as a hazard analysis, and it does not take into account the duality of the control systems in a security conflict. This is what you're actually looking at with two actors antagonistic towards each other. They have different goals for the system, but it is the same system. The same controlled process is now being controlled by two actors that their actions are not independent of each other, and there's overlap. The causality of the actions of one causes a reaction to the other, and vice versa. And the feedback is mixed. Now, I've just overlaid Colonel Boyd's OODA loop over that shared environment, and you see at the where there is overlap, because observations and actions of one mix with the observations and actions of the other, and feed into their orientation and their decisions. And that's what makes this loop such a strategic point, that getting control of it for yourself and for the attacker, as a from a defender's perspective, making sure that you don't lose control of your loop, or from an offensive perspective, making sure that you corrupt your opponent's loop. And that can be the corruption of the opponent's loop, still can be a blue team attack, because you're adding things like your firewalls, your honeypots, your other things that delay his decision making and make it harder for him to navigate through. And he's got to change tactics a lot, which slows him down. Oh, it looks like I'm back. We just had a glitch there. And thinking of glitches, when we look at a signal coming in from a sensor, there's something called aliasing that happens when when you're not capturing enough images or enough samples of it to capture that fundamental frequency. And it will look like you've got a good image, you've got a good, validly expected input, but because you did not capture enough images of it, in enough samples, you'll lose so much of your actual signal. And that happens because of that. There's the Nyquist frequency and sampling theorem that is hard, and it's a physical law. You can't get around it. But as an analog to that, it also happens in the decision cycles. If I don't see the changes in the environment fast enough, I'm not able to do that observation. If I'm not observing enough, I'm not able to orient to reality. And my decisions are now based on past information, not current information. And because they're made on bad data, they're bad decisions. And my reactions are going to be bad. And that is somewhat we have a term called the fog of war. It's that disorienting notion that you're not able to keep up with everything going on. And it is very similar to this. So, and if you go back to here, at this, if you're operating at the same speed, both the red team and the blue team are experiencing it at the same level. You're both interfering with your opponent's decision cycles, and you have only part of the picture. Now, but let's say you speed up one of these. If you speed up one, slow down, or because you're also bound with the same physics between them, you speed up one, by, let's say you speed it twice. Now you are seeing everything that your opponent does, but he's only seen half of your movements. And your movements are completely lost to him. And by doing that, and by designing your system to allow you to do that, you've taken over the whole game, and you are able to make opponent in this conflict start failing to make good decisions. And it is that ability to control the decision-making cycle that gives a blue team the advantage or the red team the advantage. And understanding that as a critical point, whether or not it's at the PLC to motor driver to physical system to sensor, at that low level, level one of the Purdue model, or it could be at the high level with your policies and procedures or law, that same circular feedback is manipulated. And because of you can scale it from small to huge, and put it both on technical controls and non-technical policy controls. Being aware of that dynamic is crucial for defending any OT system. So, in conclusion, we need to be able to model the feedback and the learning cycle that all people learn and all people go through. And even our smart systems that have an automated control, we design them to emulate that. And they go through that learning process, a cyclical refinement. And so a threat model that does not consider that learning is inadequate to properly address real conflicts, and it leaves gaps where attacks can come through. Also, at the heart of security versus safety is an intelligent learning opponent who also has a decision cycle. And knowing that and taking that into account gives you the ability to offset it and know what types of things to expect and know your own limitations in light of it, because whether you can take advantage or he can take advantage is not always determined by your microcosm of your perspective, and gaining that, but having a broader perspective on it will give you a decided advantage in keeping your stuff secure. All right. And now I am open for questions, and here's my contact info.
Thank you so much, Steve.
Yes, thank you. Now, obviously, it's question time. So if you've got any questions, make sure you drop them in chat. And we've got time for a couple. We'll see.
Hey, my question again. I always get the first question. It's my specialty. Okay, so this has happened to me in some terrifying instances, but also some benign instances. So I'll let you pick if you have any good stories. But have you ever had any issues with analogies being confused or misunderstood when applying OODA, specifically to OT and ICS?
Occasionally, most of my, since I'm a federal defense sector practitioner, most of my audience is at least nominally aware of the Colonel Boyd's work, since it was widely published in the last in the 1980s, 90s, and coming up in the early 2000s. That was in all our coursework. So the familiarity with that is there. However, applying it into this domain is it makes a lot of people scratch their heads, because a lot of the non-technical people are familiar with what's going on in that, but they don't see how it applies to a technical situation.
Thank you.
If we have any more. It's more of a comment, but
yeah. So Barbara Cosgriff says, "Awesome presentation. I haven't heard anyone articulate OODA in quite a while. Love it. Thank you, Barbara."
Yeah, I had a question myself. It was more along the lines of actually how to go about applying it. I suspect the answer is probably a bit time-consuming. But also, I'm not familiar with the OODA itself, so that's.
You apply it like you are familiar with a closed-loop PID
Sure.
control system.
Mm-hmm.
OODA is a closed-loop control system. But it takes into account an adversarial control system as well, and you are doing and you apply your standard tools, your firewalls, your technologies, but in such a way as to protect your own ability to make decisions and to remove the adversary's ability to make clear decisions, to slow him down while you take more observations. And so a lot of the principles are piecemealed. Like if you go through like the MITRE ATT&CK framework, you take all those little pieces, but then how you actually orchestrate them to work together is where the beauty of this is.